Hello there. In this video, we're going to look at Chapter 9. So Chapter 9 looks at special topics in regression. We're going to kind of do just a flyby of this chapter. So we're going to hit the main ideas, but we're not going to cover it in great depth. And this chapter, we're going to primarily focus on what is called logistic regression. And so the idea is once you get past this chapter is that you could run a logistic regression analysis, but not necessarily all of the mechanics that are involved with it. So just kind of keep that in mind as we go through. So again, as it says here at the top, we're not going to cover sections 9.2 to 9.4. And we are going to primarily focus on section 9.5, which covers modeling qualitative dependent variables. So up to this point, when we've looked at our response variable y, it's always been quantitative. So in this section, what we're going to look at is when the response variable y is a qualitative with two levels. So in other words, it is a binary variable. So just as we did with qualitative independent variables, remember we set up dummy variables to represent that response variable. We're going to do the exact same thing here. So notice here we go. Our statistical model is going to look the same as it did before. We're going to have our response variable. We're still going to have all of our explanatories. What changes now, though, is when the response is binary. So in other words, y is now categorical. What changes is the expected response. So you'll remember before we had the expected value of y was equal to this, and that's what we had before, but now we're going to set that equal to pi. And the reason we set that equal to pi is going to be equal to the probability that y is equal to 1. And remember, y is a dummy variable, so y can only be 0 or 1. So just like before we thought of 0, kind of like as the base case, you could think of something similar here, and we're interested in the probability when y takes the value 1. And so that's why we're going to set this equal to pi. Now, if we were to try to do an ordinary least squares approach to this method, we get the following problems. Our errors are no longer normal. And so this assumption is violated because the response y, and hence the random error epsilon, can only take two values. It's 0 or 1. If you predict that you're going to have a 0, but you had a 1, you've got a difference of 1 in your error. And so our errors are no longer normal. And remember, that was one of our assumptions from before. We have a problem with the equal variance assumption. So unequal variances. It can be shown that the variance here is equal to pi times 1 minus pi. And this should look familiar to you. If you remember back to your intro stat class when we looked at Bernoulli random variables or a binomial, you saw before, instead of a pi, you had a p, but if you'll remember in some of the formulas you've seen before, you've seen p times 1 minus p. It's that same idea of where that's coming from. And since pi depends on the values, it's not going to be constant. And then problem 3, restricting the predicted response to be between 0 and 1. Since the predicted value y hat estimates this piece right here, which is a probability, we'd like y hat to have the property that it's always restricted between 0 and 1. Again, because probabilities are always restricted between 0 and 1. However, if we use the least squares regression, there's no guarantee that the predicted values are going to be in that range, and so that can lead to nonsensical results. So given all these three problems, instead of using the methods we used before, we're going to fit a model that's specifically designed for binary response, and it's what's called a logistic regression model. So this is a special type of regression model that's used when you have a binary response variable. And so section 9.6 focuses specifically on logistic regression. So when you have logistic regression, the relationship between a qualitative binary response y and a single predictor x is often curvilinear. So we no longer have that straight line linear relationship that we saw previously. One of the particular curvilinear patterns we frequently encounter is the S-shaped curve that you see right here. And so the model is given by this formula right here. It was originally developed for use in survival analysis. And so in survival analysis, your response Y, that's whether or not a person survives. So they code it as a 0 or 1, depending on whether or not the person survives or they died. And then the curve has asymptotes again at 0 and 1, and the reason for this is remember that the expected value of Y is a probability here, so we would like our curve here to be restricted between 0 and 1, and so this has that property that we want. And so in general, here is how we can write this model. And so this looks different than what you had before, but remember that previously what you had was the expected value of Y, and then you just had this piece in the top. What we're doing is taking a transformation of this piece, and that transformation makes it so that the expected value of Y is always restricted in between 0 and 1. So notice in the case where you've only got one X, you get exactly what we had up here. And so the logistic regression model is not a linear function of the betas. And it's not linear because notice we're taking a function of the different betas. So obtaining the parameter estimates of this regression model, it's numerically tedious and requires sophisticated computer programs. And so we're going to look at two different general approaches that you can do in the computer. We're obviously not going to do any of these by hand. The first one is what is called the least squares estimation using transformation. And so here we've got the expected value of Y is equal to pi, again, where pi is that probability. So all we're doing for this line is we're substituting pi in for the expected value of Y up here. And using transformations, what we can do is we can show that the natural log of pi over 1 minus pi is equal to, and notice this is the piece that we're used to seeing on the right hand side of the equation. So we let pi star be equal to this piece right here. And this is what's called a logit. And so using the transformation method, we find that pi star is equal to this piece. And notice this is very similar to what we would see previously, except you would just have a Y here. So that's why this puts it in a form that we've seen before. This is linear in the betas, and so we can use the methods that we've used before. And then what we can look at is the odds in an event where Y is equal to 1, and notice odds are equal to pi over 1 minus pi. So what this gives us is the probability Y is equal to 1 divided by Y is equal to 0. So let's look at an example here. So suppose that pi was equal to 0.6, and the odds of Y equal 1 occurring would be equal to 0.6 over 0.4, which is 3 to 2. The transform model, pi star, equal to this piece right here, is a model for the natural logarithm of the odds of Y, and it's called the log odds model. So this transformation gives us this log odd model. And so the method succeeds in linearizing the response function, but there are still problems. And this method only works when we have replicated observations for each combination of the x's, and those number of observations at each combination is large. So in order to use this particular method, you have to have these conditions. Now, just as always, we're interested in the interpretation of the parameters, so let's look at that. Looking at pi star, and we're just going to write down what pi star represents. So now we're going to write out what the interpretation of the different betas is. So beta I in this case is going to be equal to, I'm just going to write this down, then we'll talk about it. All right, so notice here, this interpretation, if we ignored just the log odds pi piece, so ignore that for a second. So it's change in blank for each 1 unit increase in xi, holding all other xi's fixed. Notice this is very similar to what we've said before, but before we had the change in the response variable for each 1 unit increase in xi. Well, our response that we're modeling right now is the log odds, or pi star. So this is the same interpretation for the beta i's that we've seen before. And what we can do is we can transform the beta i's to be equal to e beta I minus 1. And that is going to be the percentage, or percent change rather, in odds pi over 1 minus pi for every 1 unit increase in xi, holding all other xi's fixed. All right, so that was the method of transformation. The other method that we could use is what is called the method of maximum likelihood. And so this is a technique that does not require, so notice this one does not require the data to be replicated. And maximum likelihood estimators have desirable properties. And so to actually learn more about maximum likelihood estimation, that is an STA 521. And so the maximum likelihood estimators are the parameters in the overall model. What they do is they have an approximate chi-square distribution, and they look at the data that you have, and what they do is they look at all the potential different maximum likelihood functions, and they maximize them. And that's what helps you get the parameter estimates. But again, not going to go too much into that, just want you to know that that is the other method. So let's look at an example here. So consider the problem of collusive or non-competitive bidding among road construction contractors. Recall that contractors sometimes scheme to set bid prices higher than the fair market or competitive price. Suppose an investigator has obtained information on the bid status, fixed or competitive, for a sample of 31 contracts. In addition, 2 variables thought to be related to bid status are also recorded for each contract: number of bidders, x1, and the difference between the winning lowest bid and the estimate competitive bid, called the engineer's estimate, x2, measured as a percentage of the estimate. The data appear in the following table, with the bid response status y recorded as follows. So notice here we've got bid status, and in our code that's going to be denoted just as status. Notice it is binary, it just takes the values 0 and 1. Next, we've got number of bidders, and this is going to be denoted as num bids. And then due test, that's going to be the difference between the winning bid and the engineer's estimate. All right, so on the next page, we've got some SAS output. So here's the SAS code. This is what it looks like to run a logistic regression model in SAS. So looking here, first notice that all of the data entry, that's the same as what you've seen before. But now instead of running proc reg, you're going to run proc logistic. And so proc logistic is what's going to run the logistic regression model. Here is the model. You know, as you've got status is equal to num bids and due test. And then we've got some other output here that we're requesting, but this is very similar to what you've seen before. And then the proc print statement here is just printing everything for us. I'm going to kind of just go through the output, but we'll come back to it and look at it more. So here is the output in terms of your model fit here. You've got some AIC, SC. You can ignore these for right now. These are just statistics that help you measure how well the model fits the data. Down here at the bottom, we've got some different tests, and we're going to come back to this. Looking at page 7, this is going to look more familiar to what you've seen before. Notice you've got your intercept and an estimate, and you've got the coefficients for the two different predictors. We've got some more output on the next page, which I'm just going to gloss over this output for right now. We've also got some output here in terms of the observations, and then we're going to get some predicted intervals here, or prediction intervals, and again we'll come back to this. On the next page is how you could perform this analysis in Minitab. So up here at the top are the different steps that you would click through to get to the Minitab, or pardon me, to get to logistic regression. And then very similar, here is the output. And so we're going to have several pages of output here. We're going to have some output on how to get the prediction interval. And then finally, we've also got the R code to get this. So notice instead of using the LM function for R, you're going to use what's called the GLM, which stands for Generalized Linear Model. And again, you've got all your R output. All right, so we're going to answer some questions based off of these different outputs. So first of all, we've got, here's the interpretation from earlier that we wrote down, so it's just here for our convenience. So the first thing we're going to do is we're going to write down the prediction equation for the logistic regression model. So to do that, what we're going to do is we need to find our different estimates, and I'm going to write them down here, and then we're going to go back through the output and I'll show you where they are in the output. All right. These are going to be located on page 7 is where we're going to find the SAS output. They're going to be located on page 11 for the Minitab. And they're going to be located on page 14 for the R. So let's look at each of those different pages and see where this output is. So we'll start out with page 7. So this is page 7 that I'm showing you here with your SAS output. Notice that right here, this is where we're getting our different estimates. So this is what we need for page 14. And so here is your beta naught hat, your beta 1 hat, and your beta 2 hat. Next, we'll look at page 11 for the Minitab output. Here is page 11 of the Minitab output. And I think this may have got moved on me. Yeah, it's on page 10, so let me fix that. That is an error. We actually want page 10 right here. So if we look at the very bottom of page 10, here are the estimates we need for page 14. So notice you've got beta naught hat, beta 1 hat, and beta 2 hat. So again, this is page 10. And then finally for the R output, that's going to be located on page, and I've got 14 there, that's wrong. I think all my pages got shifted from what I had before, so this is actually page 13. So looking at page 13, notice here in the coefficient section right here, there are our different estimates. So we got beta hat naught, beta hat 1, and beta hat 2. All right. So now we can write out our model. So remember that the model for the expected value of y, that's going to be equal to pi which is equal to the probability that y is equal to 1. So in this case, pi is equal to exp beta naught plus beta 1 x1 plus beta 2 x2. And so notice I'm writing this in terms of the parameters, so I'm not putting in any of those values that we found yet because that's going to be the estimate. Okay, so there's our model. So now we can get our prediction equation. And just like before, when we used y hat to denote our prediction equation, now we're going to use pi hat. And what I'm going to do for each of the betas in the model is I'm going to plug in their estimate. Right, so again, the idea is very similar to what we did before. It's just now we have a different equation that we are working with. Right. So we can answer some questions that are very similar to what we've done before. So the first thing we're going to do is determine if the overall model is adequate. So you'll remember before we used F statistics for this, we're actually going to use a chi-squared statistic in this case. We're going to assume that the assumptions have been met. The assumptions for logistic regression are different than that for regular regression that we looked at before. And in fact, finding the assumptions for logistic regression is rather difficult. There's not really a consensus on what all of the assumptions are. So we're just going to gloss over that and assume that those have been met. So under the null, we're going to have that beta 1 and beta 2 are equal to 0. Pretty much exactly the same as what we would have done before. And then at least one of beta 1 or beta 2 are non-zero. All right, so now we need to find our test statistic for this test. So we're first going to look at the SAS output. And so the SAS output is going to be located on page 6. All right, so on page 6, you will notice that there is what is called the likelihood ratio test. That is actually the test that we're going to use here for our model fit. So this is what we need for page 15. So notice here our test statistic is 18.5377, and that results in a very small p-value. And notice that is obviously less than alpha equal to 0.05, so we would reject the null. You can find something similar looking at the mini-tab, so let's do that. So for the mini-tab, we are going to turn to page 5. Just a moment here, make sure I tell you the right page. Turn to page 11. Sorry, I've got pages everywhere, as I'm sure you do too. So if we turn to page 11, notice right here we've got our chi-square test statistic. And so that's the same thing we have using SAS, and you can do something similar in R. So obviously we're going to reject the null. So in conclusion, we can say at the 5% significance level, we have enough evidence to conclude that the overall model, oops, that's an L, that includes number of bidders and that engineer's estimate, or the do test variable, is adequate to predict status. All right, now we can interpret our beta estimates. So here, recall that beta hat 1 was equal to negative 0.7553. And then if we look at e to the beta hat 1, that's going to be equal to 0.47. And then e to the beta hat 1 minus 1 is equal to negative 0.53. And so what this tells us is for each additional bidder, we estimate the odds of a fixed contract to decrease by 53%, while do test, which is x2, is held fixed. And we can do something very similar for beta hat 2. So beta hat 2 is equal to 0.1122. E to the beta hat 2 is equal to 1.12. And then e to the beta hat 2 minus 1 is equal to 0.12. And so for this one, we would say for every 1% increase in do test, which is x2. And remember, the reason we've got 1% increase here is this variable was measured in percentage. We estimate that the odds of a fixed contract to increase by 12%, while number of bidders, x1, is held constant. All right. For part D, part D says determine if the number of bids is necessary to predict status if do test is included in the model at the 5% significance level. So notice what we're doing here. We're going to perform another hypothesis test. We're under the null, beta 1 is equal to 0, and under the alternative, beta 1 is not equal to 0. So very similar to what we've done before. But again, instead of using an f-test, we're going to use a chi-square test in this case. So the first thing we're going to do is we're going to look at the SAS output. And so looking at the SAS output, This is on page 7 of the SAS output. Notice next to num bids there is a chi-square test, which in this case is 4.9703. That's going to be the test that we use. So page 7 is going to have our SAS output. And notice that this results in a p-value of 0.0258, which is less than alpha equal to 0.05. So we would reject HO. We can also find this output in a mini tab as well as R. And so let me show you where those are. So for the mini tab is actually going to give us a Z value. And so for the mini tab output, if we look at page 10, so notice here on the bottom of page 10, next to num bids, it gives us a Z value. Well, it ends up that if you take Z squared, that is distributed a chi-square with 1 degree of freedom. And so notice, if you go back to the SAS output, what we had there was a chi-square with 1 degree of freedom. So it ends up, sorry, if we look here, if you take that negative 2.23 squared, you will get that 4.9703 or something very close to it and a very similar p-value. And then if we look at page 14, we could also find this in R. Sorry, not page 14, page 13. And so R is also going to give us the Z value, and so notice that Z value is right here. All right. So, but either way, we can say at the 5% significance level, we have enough evidence to conclude the number of bidders is necessary to predict status if do test is included in the model. All right, so the last thing we're going to do here is we're going to find a 95% prediction interval for pi for a contract with number of bidders equal to 2 and winning bid amount of 24.1 above the engineer's estimate. So again, we're going to go to our output, and remember we had output from both SAS and Minitab with prediction intervals. So we're going to look at page 9 of SAS. You could also look at page, double check this, 12 of the Minitab. Okay, so let's look at page 9 of the SAS. So here is page 9 of the SAS. And if we look here, notice it's asking us to find number of bidders equal to 2 and winning bid amount equal to 24.1. Notice that observation 2 actually satisfies both of those. So we can use that to pull the prediction interval. Now, if you wanted a prediction interval for observations not in the model, you would do something very similar to what we have done in previous chapters. All right, so here our interval is going to be 0.53645 to 0.99384. And so here we can say with 95% confidence we predict pi, which is the probability of a contract with 2 bidders and winning bid amount of 24.1% above the engineer's estimate being fixed to fall between 0.53645 and 0.99384. All right, and then the last thing that we have in this note set, I believe, is very similar to before. We can test to see whether several predictors significantly improve a model using the methodology similar to comparing nested models. So notice here we're still going to have a complete and we're still going to have a restricted model. And then we're going to go through and compare these two. The only difference is before we had that F test where we looked at 2 different ratios. Here we're going to look at the difference in the chi-square statistics. And we've got some output that follows here that has those different values. So what I'm going to do in the note set is I'm going to stop the video here, but I'm going to write this out completely so you can see it, and I will mark in the output where to find the different pieces. This is going to conclude the Chapter 9 video.